We have a new session now, which is a continuation of the session you did yesterday on conformance checking. I'm very happy to introduce Professor Boudewijn van Dongen, which already you have had yesterday. So we will continue on the amazing topic of conformance checking. So without hesitation, Boudewijn.
Thank you, Josep. Thank you. That's better, yes. All right, thank you for the introduction. And thank you, in particular, yesterday for all the questions, because that caused me to update the slides. So for those of you who are using the slides that are on the website, sort of in the background, Leah was kind enough to upload a new version just this morning that actually matches the presentation. And the slides of yesterday have also been re-uploaded, including the exercises and the solutions that were not there yet. So today we're going to talk about a little bit formal things with respect to alignments. I know there are some mathematicians in the room that might appreciate this, but we also talk about the other end of the spectrum, the application and interpretation in a bit more detail. And in the meantime, we're going to talk about more than just fitness, right? Yesterday we spoke primarily about fitness. There was a question to look at other dimensions as well, so we'll address that topic too. But first, a little bit on Petrinet theory. Right? This is familiar to maybe a few of you, but I felt the need to introduce a bit of mathematics into this presentation, because Petrinets are not just pictures of boxes and circles with tokens floating around, right? There is real fundamental mathematical theory behind this, and this is what makes them so nice for all kinds of process discovery, conformance checking technology, because on the one hand you have a very natural problem at the business level, and on the other hand you have a very fundamental sound mathematical foundation to build papers and books on. So a Petrinet is a picture of boxes and circles, but at the same time, a Petrinet also is a linear system with vectors representing the places and markings representing the tokens, the number of tokens in each place, and an incidence matrix indicating precisely what the consumption and the production behavior is of each of the transitions. So for example, transition T1 here consumes a token from P1, so there's a -1 in the matrix, and produces a token in P2 and P3, so there is a +1 in P2 and P3. And in general, there can also be +n. You never see those in process mining, but in modeling or system modeling with Petrinets, there can also be multiple tokens. So we have a marking and an incidence matrix. And the nice thing of these two combined is that you can make equations with vectors and matrices. So for example, if I fire the transition T1, something that we did yesterday visually with tokens floating around, but that simply means I'm taking the vector of the current marking with a token in P1 and no tokens anywhere else. I add a multiplication of the incidence matrix with the vector introducing which transitions I'm firing, in this case T1 once and all the other transitions not. And then I get a new vector. This is simple linear algebra. P1 is now 0, P2 and P3 have 1 token and the other places are empty. And graphically, that also means that the state space, right, the big graph that we drew yesterday, now has a transition from the state P1 to the state P2, P3. And in this model, I can continue this by, in this marking, again firing a transition. I can fire, for example, T2. Again, this is a multiplication of the marking P2, P3, the incidence matrix times the Barik vector of the transitions I fire, and I get a new marking. And you can keep on doing this to get the firing of the transitions sorted in a model like this. Now, what is not in the linear equation system is the enabling condition. A transition can only fire if and only if every input place has at least one token. Like if you just randomly would multiply matrices, you can get negative markings. Tokens, like places with minus a number of tokens. But that means that there is a relation between this marking equation and the Petrinet, but they're not the same thing. And this relation is called it's actually called the marking equation. So if you can reach a particular marking from another one, there is an integer solution to this equation here. So if I can reach m prime from m, then there is an integer solution to the equation system m plus this incidence matrix times x equals m prime, where x is actually the paric vector of the transition firings. So if I can fire a sequence of transitions, I just make this sequence into a vector, and then that is an integer solution to this particular problem. It's very trivial to see that this is the case. And if you want, you can try to do the proof yourself. It's done by induction over the length of the sequence. However, the inverse is not true. That would be cool, right? If the inverse would have been true, that would mean that we take a synchronous product, we solve this interlinear program, and we get a firing sequence of that model, which is immediately a alignment. But unfortunately, the inverse doesn't hold. So can we still use this? Now, we'll see how to use this in alignments today. So let's go a little bit into the algorithm, into the details of finding a alignment. The synchronous product that we saw yesterday nicely fits on the slide, right? That's what it was designed to do. However, in general, Petrinets might even contain infinite behavior, loops, right? But also infinite state spaces. Unbounded Petrinets, so Petrinets where the number of tokens in a particular place can grow over time, might generate infinite search spaces. So they're very difficult to draw and very difficult to find alignments for. And these are not very uncommon. Well, like we like to talk about sound Petrinets, or the term soundness was introduced earlier. But if you take an arbitrary BPMN model and you would do a naive translation from BPMN to Petrinets, you might easily end up with an unbounded model. So this is not very uncommon. So the question is, can we limit our search to only that part of the state space that is actually relevant to find an alignment? I'm going to make one assumption here. That assumption can be lifted. It was done in the original thesis on alignments, but it makes the story far more complicated. So let's assume that we do not have infinite parts reachable at distance 0. What does that mean? Well, this is a very simple example that actually has the problem. So this is a HR type of process. You advertise a position, and then the moment the advertisement is out, I can generate a number of tokens here, and this is an arbitrary number, so as many as I like. Then I can read CVs, and at some point I interview a candidate, and I can interview as many as I like, but I have to read the CV first, until I remove the advertisement and hire a candidate. It's a very simple HR process, but this model, because of the sort of loop that is introduced here, the tau transition takes this token but also produces it back, I can create an arbitrary number of tokens in this place. And since tau transitions have cost 0, like in alignments, I now have an infinite search space reachable with cost 0. Now that is a problem for any alignment algorithm, so I'm not going to assume that, we're going to assume that this is not there. In general, if you take sound models, that's a sufficient condition, right? So sound models don't have this problem. It's a little bit too restrictive, but it's sufficient. It's a sufficient condition to avoid this kind of issue. All right. The general solution is to add a delta cost, and for the numerical mathematicians here, if you do this, you run into numerical problems, right? So you get computational complexities due to the delta in relation to the large cost. So we have a synchronous product. We've seen this one before. It's the same synchronous product that we had yesterday, and now we're looking for a shortest firing sequence from the initial marking to the final marking. And this is the search space that we looked at yesterday, but yesterday we looked at the entire graph. Now, how do you find the shortest path in the graph? I have to mention this, right? So this is the original algorithm to do that was designed by Dijkstra from Eindhoven University of Technology at the time. And he came up with a technique that actually expands the search space in a particular way, sort of making a front of all the states reachable at a particular distance. And finally, you see here, the path we're looking for has cost 3. But in the worst case, this algorithm expands the entire search space until everything with a distance 4 is actually seen. Right? So here, you'll see that the things that have a larger distance, if you compare this to the search space we saw before, everything that has a distance greater than 4 is actually removed. So Dijkstra's algorithm helps us to not investigate the entire search space, but only a smaller fraction of it. Unfortunately, it's still a lot. It's still quite a big part of the actual behavior of the model that we need to look at. And this is where our marking equation is going to help us. So, what we're looking for is the shortest path in a graph from one point to another point. It's the same challenge your navigation device has to get you from A to B. It's a simpler graph in a navigation device, right? The graph is essentially 2D. And what your navigation device does, it actually draws a straight line between 2 points, and it tries to keep you as close as possible to that straight line. Usually this is actually the correct solution, but you might find sometimes that also your navigation device does strange things, right? That's because it implements a version of this algorithm. It's called A star. And A star is a technique that basically takes you, uses this straight line estimate, like an underestimate of the actual distance, the actual cost you still need to make to reach the end. It uses an underestimate of that distance to get you to your final destination. So in a planar graph, the underestimate of a distance is the Euclidean distance. You cannot be shorter than simply a straight line between 2 points. Now, in Petri nets, we don't have straight lines between points, but we can use this marking equation for that. Because the marking equation tells us that if there is a sequence of steps to get from A to B, then there is an integer solution to this equation. And every transition that fires has a particular cost associated to it. So I can translate that into a linear optimization problem. Minimize the cost times the transitions I want to fire, such that the marking equation actually holds. I want to go from the marking where I am now to the final marking. The solution I get from solving this equation is not a firing sequence, right? If there is a firing sequence, that firing sequence is a solution, but not necessarily a minimal one. The minimal solution I get here might not be a firing sequence. However, it is an underestimate for the actual path I'm looking for in the graph. Yeah? You can solve this in interlinear programming, where X says you fire this transition twice and this transition 2 times. You can also solve this without the integer part. it just becomes a worse estimator. But it's much more faster to solve. This problem is NP-complete for integer linear programming, and it's polynomial for non-integer programming, although the actual implementation typically uses an exponential algorithm called simplex. So the marking equation helps us to get this underestimate, this sort of intuitive notion of a straight line in a navigation device. And the beauty is that if we look at this, suppose I'm in this initial marking and I want to go to the final marking. Then we already know, right, this is the example we saw before, we know that the cost is, sorry, I'm laughing because we're going to have less coffee cups later today. We already know that the cost is 3, right, to reach this final marking. But if I solve this linear equation system, I get this solution. It tells me you fire application submitted synchronously, you do a log move on this call, then synchronous send offer, synchronous call, synchronous approve loan, synchronous transfer money, and somewhere in the meantime you have a check documents and an offer accepted. Both of them are model moves. Cost of this is 3, right? The check documents, the offer accepted, and this call actually have a cost of 3, so this is a minimal solution. However, I hope you spotted that this is not a realizable sequence. I cannot actually execute these transitions one by one, right? I cannot make a sequence of these transitions because the whole marking equations that I used ignores the ordering. And the problem is that it wants to do this call synchronously and this one asynchronously, while the solution we saw before is actually the other way around, right? But this ordering is something that the marking equation doesn't show you. It does, however, tell me that there's no point in trying to find a solution that has less than, like, a lower cost than 3, because the marking equation says the minimum is 3, so the actual cost must be higher than that. Suppose we do this, and we now executed 2 log moves somewhere in the search space, right? Somewhere in this search, when building the search space, we executed 2 of these log moves. And now we're in this marking. And we asked the marking equation for an estimate of reaching the final marking. We now get this vector back. So it says, in order to reach the final marking from the current state, you need to make at least cost 3. 1 for application submitted, 1 for check documents, 1 for offer accepted. And since I already executed 2 steps, I have a total cost of at least 5. Right? In order to reach the final state from this point, I will reach it with a cost of at least 5. Now, and that is information that our algorithm will be using to schedule which states are more likely to get you to the correct destination. This is also how your navigation device works. It moves from part of the street, right? It builds sort of a network around this straight line, sort of guessing which is the most likely path taking you to your destination as quickly as possible. Same here. Suppose we executed part of this model again. We now have this state after check documents and after call. And now we get an estimate from the marking equation. And it will tell us, well, in order to reach the final state, you will have to execute offer accepted, call, so you get a final marking of at least 3. And interestingly enough, in this particular case, the solution we get is a realizable firing sequence. So now we have a situation where we have a marking where the ILP solution of the marking equation actually corresponds to a realizable sequence of firing transitions. And that's good news because now we can stop looking. The moment this happens, the techniques will actually simply try to sequentialize the paric vector. So there's no computation cost involved anymore. So what does this lead to? Okay, sorry, we have one more example. Suppose we're here, and again, we ask for a solution, and then we know that we need to make cost at least 3, but again, we have a non-executable sequence, because it will try to synchronize on this call, and we've seen before that that is not possible. So how does this help us? If we look at the full state space again, this is the entire state space, right, that we saw before, but now, for all the states I just showed as an example, I indicated this heuristic, right? What is the minimal cost to go from this marking to the final marking? So in the initial state, our heuristic says the minimal cost to go to the final marking is 3, and that's true because we already know it's here, right? With cost 3, so we know it has to be at least 3. However, if I do the 2 log moves first, and I'm here, the heuristic, the minimal cost of reaching the final marking from there is 5. Oh, is 5. So that means if you look at that state, you should really not look at it any further until you actually reach the point where everything else would lead to cost 5. And this is how the algorithm progresses, and in the end, in the worst case, this is the fraction of the search space it would actually investigate. And this is the worst case expansion. In practice, it would not even do this. So in practice, this technique will reach this marking here, and from that point onward, it will just have a straight line to the finish, because then it gets a sequentializable vector. But this is a sort of the worst case expansion. It includes all the states where the heuristic is already much higher than the actual distance. All right? Now, this was a bit of the mathematics. Then we also do computer science here. So what is the actual algorithm as it's implemented in PROM? Unfortunately for everybody, it's complicated. The complexity class, I talked about it yesterday with somebody, is a p-space complete for most of the models. If you include unbounded models then and unbounded models, it can even go to x-space complete. But for general sort of sound Petri nets, we have p-space completeness here. But most of the steps in this algorithm can be implemented fairly efficiently. The complexity here is really in the so not in the individual steps, because this is sort of polynomial for linear programming. All these things are relatively efficient, but in the end, because of the sheer size of the graph that you have to look at, the problem does scale very poorly on models with lots of parallelism, lots of large state spaces. This is why many of the commercial tools also do not have an implementation of this. I remember in the early couple of years back with Solonis, they showed us that they implemented this and they asked us to play around. So we put some models like the one I just showed you for the hiring service and sort of saw what happened. We broke the cloud. Of course, it was a test cloud, but still. And similar for a recent paper, I was reviewing. Also, the authors made a cloud implementation, and they asked the reviewers that they could test the cloud implementation. Well, I tried, and it broke. So it is a complicated problem, and we're still very much, as a research area, also looking for better ways of doing this. A star is great, but the heuristic we're using is relatively expensive, and we do not really have good alternatives for this particular heuristic. It's either 0, meaning Dijkstra. 0 is, of course, always a lower bound for the remaining distance, and that's Dijkstra's algorithm, or we have a fairly complicated estimator, interlinear programming or linear programming, but something in between. If you're interested, we should really think about that. All right. That's it for the algorithms and the mathematics. So let's look at more than just fitness. Right? I like fitness, I like alignments, but there's more to life. So conformance checking, as we already discussed yesterday, touches on the relation between a model and an event log. And models and event logs, they relate to each other in more dimensions than just fitness, right? With fitness, we saw in the conclusion yesterday that you can always make a perfectly fitting model. Now, I included this slide at the request of one of your colleagues yesterday. So, do you have the airplane slide? Yes, there's the airplane slide. Like the relation between an airplane and the air it's flying in is characterized by 4 dimensions, right? A plane generates lift to beat gravity, it generates thrust to beat drag, and it has a stabilizer in the back to make sure that it doesn't fly in circles, because the actual point at which all these forces work is not in the center of the plane. So that's how a plane flies, very simplified. This is also how process models and event logs interact. We have fitness, but we also have precision. And we also have simplicity and generalization. And these are 4 dimensions of relations between observed and modeled behavior that we will talk about. Well, maybe not so much about simplicity, that's more a model property. What is important to realize is that all of these metrics that you might encounter in literature, and there are many, many metrics, all of them depend on parameters that keep them sort of balanced against each other. So try never to interpret a metric without considering the parameters used to get to that metric. And the parameter is also which actual algorithm was used, like A star or alignments, token-based replay, right? All these kind of things. So what are fitness and precision and generalization? So fitness we've seen, right? We understand this. You guys now have a clear understanding. It's the amount, it's the fraction of the behavior in the log that is explained by the model. That's very easy. It's sort of recall. But how about precision? So precision is the fraction, like intuitively, it would be the fraction of the model's behavior that is covered in the event log. Right? That's how you would do it in data mining. Precision in data mining is just the intersection of the log and the model's behavior divided over the behavior of the model. Unfortunately, most models' behaviors are infinite. The moment you have a loop in your model, you get infinite behavior. So that would mean that in the pure traditional sense of precision, precision is always 0, which is, of course, not the case. So there are metrics, we'll talk about a few of them, but it's not a fully solved problem. So if you want to work on conformance checking, there's plenty of things to do in precision. Then generalization, we have absolutely no idea what it means, but we need it. Because I can easily draw a process model. This was nicely shown, by the way, by Joost Buys in his PhD thesis. You can easily draw a process model that is perfectly fitting and perfectly precise. It explains exactly the event log and nothing more. Right? You take your event log, you translate each event into a transition, you put places between them if they belong to the same trace, and in the beginning you made a decision which of the traces you're going to execute. That model is perfectly precise and perfectly fitting for every event log. It's completely meaningless, but it matches the 2 dimensions. Generalization has to do with what we feel is good modeling practice. And we'll see an example of generalization later. Simplicity is mostly considered a modeling problem, but I think you've seen this. The directly follows graph is a very nice, intuitive, simple model that even non-process mining experts understand intuitively. So that's simplicity. Petri nets, not so simple. BPMN models, the basics are simple, but once you go fully in depth of all the nitty-gritty details of what you can do with BPMN, I would argue they're more complex than Petri nets. EPCs, anybody heard of these things? Very nice to look at, beautiful colors, very easy to interpret, impossible to interpret by a computer. Right? So simplicity is a feeling, and we're not going to touch too much on that topic. So, precision, right? I mentioned already, you could argue precision is log, the intersection of log and model divided by model, but in most cases, models are infinite. You've seen region theory this morning, a little bit, right? So the original region theory, as it was developed, let's say in the 70s and 80s in the Petrinet community, what this theory did was they made a maximally precise and 100% fitting Petrinet. Maximally precise in the sense that if you get a result, it's not possible to add places to that Petrinet without at least breaking one of the observed sequences. But they didn't talk about logs, they talked about specifications of systems. So their input was different, was not a sequence of, or a collection of observed sequences. Their input was a full specification of a system in terms of what it should do when, and then you translate that into a Petrinet. Now, then you want a fitting and maximally precise model. That's what language theory does. These models also do not have loops, right? So they guarantee that loops are bounded. The region theory you saw this morning is already an application of that original founded theory in the context of process mining, right? Intuitively, what does precision mean? It means that your model can tell you if you removed something from the data. Right? That's a different interpretation of precision. So you take a data set, you have a model, and now a very precise model, if you take one trace out of your data set, that model will be able to tell you which trace that was. Right? That's a very precise model. There are two precision techniques I would like to show you. So one is the original work developed by Jorge Munoz under Josep's supervision at the time. He looked at what we call escaping edges precision. So he said, well, let's see how model and log work together. We take the event log and translate that into a tree of sequences. Right? So if two traces share the same sequence, we map them on top of each other, so you get a tree structure. We take the same tree structure, but now from a model point of view, and then we see where there are points where the model can escape the observed behavior. Right? So here we have a tree of sequences. Here we have a similar tree coming from this model, but there are points where the model can do something that was not observed. And then you can do a counting game. You can count how often this happened with respect to the observed behavior. And that gives you a precision number. Again, a value between 0 and 1. Yeah, so there's a metric, escaping edge precision, that does this on any event and model, and you should essentially see it like this. So we have the behavior of the log, we have the behavior of the model, and we are looking like where can we cross the boundary of the observed behavior and cross it into the unobserved part of the model. You can also do this on models that are not fitting, because the biggest problem here is you're comparing observed with model behavior, but you can only compare this properly if these two, at least one is a subset of the other. So what you could do is to use alignments. You do, let's look at this example. We have a couple of traces, a process model, and fitting traces, meaning alignments were made for these observed sequences, and then you take the top part of the alignment, which is the correct firing sequence, and you use that to build this escaping edge abstraction. You get different notions of precision. If you do not use alignments, then the prefix tree looks like this. If you use one alignment, meaning you just take an arbitrary alignment, you pick the best one that the algorithm gives you, you get this, for example. You could also use all possible alignments. Like we have a trace AD, and there are two ways to align this. You can do a BD, where B is the model move, or a CD, where C is the model move. Theoretically, very nice exercise. You can you get then a different graph, like here. In practice, this doesn't really work because there are very, very many optimal alignments, right? Especially if there is some parallelism in the model with respect to the log moves, you get really, really a lot of different alignments, and there is essentially no real algorithms to compute them all. Like even getting a representative for each class is difficult. But in theory, you can do this. And again, this is a parameter. Which one do you use? How much computation time are you willing to spend on it? And they might give different values, different metrics. Now, I don't want to actually talk about precision in terms of an algorithm. I want to install an intuition. So I'm going to ask you a bit of an exercise. We have 3 models here, A, B, and C. And we also have a short event log that I stole from the process mining book. So which of these 3 models, well, no, for yourself, just spend a few minutes to rank them in terms of fitness and precision for this event log. Yeah, please. Yep. Okay. Yep. Okay. Other opinions? Yeah. Indeed, yeah, it does. But how about precision? All right. So you're absolutely right. So all of these models have perfect fitness. So all have fitness 1. So all of these 3 models can actually produce this event log. That is so A is the model we've already seen a few times. B is the flower model, but now made into a workflow net using tau transitions. That remark was there yesterday. And C is just a translation of the event log into the trivial, perfectly fitting and perfectly precise model. It's completely useless, right, to analyze, but it is perfectly fitting and precise. So C is definitely the most precise model. Right? This is just the event log. A is a little bit less precise, and then B is completely imprecise. All right? 2 more. I had fun drawing that one, by the way. Yep. Yep, this one. Well, that's what the alignment technique would solve for you, right? Because I would get a synchronous product that is, so suppose we take the first trace, I would get a synchronous product with 5 synchronous A transitions, and in the end, only one of them will lead to cost 0, all the others will lead to a much higher cost. So the search space of the alpha algorithm using A star would actually be very small. In the initial state, it finds 5 predecessor states of the synchronous A's, and 4 of them will have a very high cost according to this interlinear program or linear program, because it cannot match the sequence with the remainder here. And only one of them will have cost 0. So it will continue with that one, and then it can actually sequentialize the Parik vector. So it's very easy to do these alignments, and the choice which A to do is made for you by the algorithm. In token-based replay, you can't do this. Yeah, so token-based replay we cannot do on this model because we do not know what A to fire. So you would have to look ahead a few steps and would probably still be able to figure this out, but it's heuristics. So it might make the wrong choice. All right, 2 more models. Slightly more complicated. So maybe a little bit explanation of what the right model does. It initially makes a decision where in the outer circle it starts, and then it goes around up to the same point, and there it stops. Well, it can go around multiple times, but it stops where it started. That's how this model is built. It's tricky, right? I told you that precision is not a completely solved problem. And this is a nice example of why. So what you're intuitively struggling with, I think, is, but this model has nothing to do with the log that we looked at. So you're asking me to say something about precision, but how do they relate? Right? The first one, at least, is a translation of the most frequent trace. So you could argue that this is a very precise model. Right? It actually explains only one sequence of steps. In terms of escaping edges, there are none. Right? But the problem is that all the other traces are not explained. So how do you say something about the precision of such a model if it only explains a very small part of the observed behavior? And this thing here does not explain anything that we've observed. Well, okay, it has the same alphabet. That's it, right? It has A, B, C, Ds. But it can fire the sequence A, B, C, D, E, F, G, I, H, I, or the sequence A, B, C, D, E, F, G, H, I, A, B, C, D, E, F, G, H, I, and so on. So it can do an arbitrary number of iterations starting at any arbitrary point. And the reason we include this model is that it's a nice example of all these sequences being part of a separate, completely separate component or subset in the state space. So it has very weird behavior when you look at the search space of this model. Like all the subsequences may be overlapping, but they all take place in different parts of the search space depending on where you started. That's why it's included. So how do you deal with this? Well, we don't really know. With fitness we do know, right? A is most fitting because it at least explains something. B is not fitting at all. It's not 0. You can find alignments, but it will be very close to 0. A is precise, and this is a slightly different reasoning. If you remove this one trace from the event log, it can accurately predict that that is the one you removed. If I remove this trace from the event log, the first one, then it can actually predict that is the trace you removed from the data. If I remove the second trace from the event log, it will predict that you did not remove anything. And so does for the third, fourth, and the fifth trace. So there the prediction fails. But at least for the first trace, it's right in 1207 cases. That model, no matter what I remove from the event log, it will not be able to predict what I removed because it doesn't show, it doesn't present or represent anything of the log. So that's how I would argue, more precise and less precise. But always in the context of fitting traces, right? You have to relate the two. So fitness is by far the most important dimension when you're trying to explain the relation between the event log and a process model. And also this was shown very nicely in the work of Joost Buys. What he essentially did, he painstakingly took event logs. He used a genetic algorithm to construct process models, and he set to the genetic algorithm to optimize for 1, 2, 3, or 4 of the dimensions. And he had metrics for all 4. And they were weighted in a particular way. And what he showed is if you remove one of the dimensions out of the equation, so you set the weight to 0, the genetic algorithm will find the model that you do not want. So, genetic algorithms are great to disprove any of your thoughts. Right? Whenever you feel like, would this work? Give it to a genetic algorithm, and it will tell you if there is something that is problematic, it will find this. So he showed that you need all 4 dimensions, and he showed that the weight of fitness is most important. Sorry, yeah? Yes. Yeah, then my answer, the question here is, if I take let's say the sequence model for the least common trace, right? What is then the fitness of one versus the other model? And there I would argue it very much depends on the technique you choose to compute fitness. I would have to do the calculations for example, for alignments to figure out what the fitness would be. And you can also do this with the token replay. I mean, in this case you can, right? But then it depends on the metric, on the parameter, which of the 2 models is rated as better fitting. So it depends. All right. Now, how did I now? When we looked at the last example, we looked at this predictive ability of being able to predict which trace was removed. And the work that actually does this is work I did together with Thomas Chatin and Josep a few years back, and we came up with this concept of anti-alignments. I'm not going to give you the algorithms, but the idea is actually very nice. An alignment is a sequence in this model that is as close as possible to the observed sequence. Right? That's what we're looking for. The anti-alignment is the opposite. So it is the sequence in the model that is as different as possible from the log. Not from one sequence, but from the entire log. That's what the intuition is behind an anti-alignment. So we take a model and we try to find a sequence that is as different as possible from what we have observed. And we came up with that idea in the context originally of precision, precisely with this in mind. If you remove one element, a precise model would be able to predict which it was. So we are looking for the trace of the model that is different from what we have observed. That's the anti-alignment here. It's a far more complicated problem than alignments, because you have to look at the entire log at once. You can't look at it trace by trace. Thomas did that very nicely in set theory, so set solvers he used. I can't even read the formulas he writes these days, but it's really beautiful from a computer science point of view. So can you tell me for which model, like for this log and this model, what is the trace that is not in this log? There are so many? No, but so is there a trace in this model that is not in the log? In this, so it has to be a fitting trace, right? So what is a fitting trace in this model that is not in that event log? No, that is not a trace, right? Because if I fire A and B, then I need to do D as well, and then I get the first trace. The second one, A, firing C, then D, G, H, F, and I. So this is a fitting event log. It's a fitting model. Yeah? A, C, D, H, F, I. That's the last one. Indeed. So A, C, D, G, H, and then the D, F, and I. So I've seen the D, G, H, I've seen G, D, H, but I have not seen G, H followed by D. Right? This is one of the alpha algorithm still produces this model, by the way, because it has seen all the direct succession relations. Right? Remember, the alpha algorithm builds on direct succession. I've seen all the direct succession relations, but I've not seen all the possible sequences. And this is one that I haven't seen. So if I take now a trace out of this log, for example, the first one of length 5, and I ask an algorithm, please give me a sequence of length 5 that is not in this event log. It will actually give me this one. There is no other sequence of length 5 because that is longer. For these two, if I take this out, it might actually predict wrongly. It might give me that one. Yeah? Because it has the same length. For these two, it will also accurately predict. So this is actually a technique that works relatively well if you consider precision to be precisely like you take one out and then you try to predict what you took out. Unfortunately, it's computationally extremely heavy, right? So yeah, it works well, but you need to have the time to compute it. All right, then generalization. We already felt maximal fitness and precision is not enough. But how do you, what does it mean it's not enough? You could argue that the model with all the sequences in there has too many transitions. That's a simplicity constraint, right? You would like to reduce the number of transitions. One way of doing that is collapsing the presets, right? Then you already get fewer. But is that enough? Now, for generalization, you should think of modeling again. So when you were told or taught to make process models, when we are talking about the alpha algorithm, when we're talking about region theory, what are we aiming to do? We aim to discover a model, we aim to produce a model that abstracts from reality. And the two concepts that do this in process modeling are essentially loops and parallelism. Parallelism says you can do these two things in any order, and loops say, well, you can do this more than once or more than 0 times. We are not saying if you introduce a loop into a model, we're not saying you should do this infinitely often, right? We are doing this because we say, well, this can happen once or twice, maybe in exceptional cases 3 times. And when we introduce parallelism, we're also not saying you should always decide whether you do it in one order or the other. We're just saying, well, when you execute this process, it doesn't matter in which order these steps happen as long as they happen. It might in practice very well be that you always execute them in the same sequence, but you don't have to. These are concepts that generalize, and they have 2 things in common. Loops and parallelism have in common that you're introducing sequences in the behavior, without introducing too many states. This doesn't hold for parallel, like 2 things in parallel, but from 3 onwards, you're introducing more sequences than states in your behavior. And in one technique that actually measures this generalization uses this concept. So again, anti-alignments, you try to find a sequence of behavior that is not actually in your data, and you then measure whether this sequence is actually part of the state space that you already observed, or whether it's completely new, or whether it's taking place in a completely new part of the state space. And a model that does this, so you have a new sequence, but visiting states you saw before, is generalizing better than a model that does this. You only visit states, or you visit new sequences in completely new states. And this is why this cogwheel model we saw before comes into play. That model does this, right? You can always find a new sequence with a complete new set of states. So that's very poorly scores very poorly on generalization. All right, but there's more. We like this model the best. It's fitting, it's fairly precise, it nicely generalizes by putting D in parallel to the GH construct, and it's also simple, right? If you heard about patronage for the first time this week, you can understand this model. So this we like. How can we argue that we like this? Well, we use metrics for fitness, for precision. We only saw 2 metrics in detail, like token-based fitness and alignment-based fitness, but there are many, many more, both for fitness and for precision, some for generalization, right? And there are hints in the book on where to find those. I can't tell you which one is better. I can only tell you which one works best for you, right? You do an exercise, you look at models, and you can say, well, this one works better for me, it's more fitting on this particular metric with these particular parameters. So if I can't tell you objectively which metric is better, how do you then evaluate conformance checking? If you're going to do research in this area, how do you compare this work against others? This is a challenge that we struggled with in this field for a while, and some people are still struggling with this, because we tend to, as computer scientists, we tend to be biased towards a practical evaluation of things. We tend to say, okay, I have a benchmark, I have a log and a model, and I know what the fitness should be, and then I compare it with this metric, and my metric reports this more accurately, it reports it quicker, it reports it in a more intuitive way, it looks nicer. Right? These are not arguments I made up, right? These we took out of papers. So I did case studies and the company liked it. Right? So these are practical evaluations of metrics, and I would argue don't do this. Don't start competing with your fellow PhD student on the computational speed of your implementation. Right? We're not here to solve computation challenges. Some people maybe, when you're in algorithmics, you try to find sort of the fastest way, the best and the most beautiful data structures, and you can lose an enormous amount of time doing this, and it's fun sometimes, but that's not what this is about. We do not understand precision well enough yet. So let's not focus on the computational complexity, but let's focus on the problem. So how do you evaluate it? Well, there are 2 ways. One is theoretically. Like the anti-alignment work is a very nice example of that, because it's simply proven to report something correctly, right? It works. Computationally complex, but it works. Same with the alignment algorithm. It's proven to be correct. It does exactly produce a sequence of the synchronous product with the lowest cost. You can also compare by saying, well, I'm visiting fewer states. I found a smarter way to go from A to B. Right? This is how Garmin and TomTom competed in the beginning of the portable navigation devices. They were competing on the best algorithm to reach point A from point B. These days, they're competing on the best traffic information. So actual constraints on the roads, live, to get you from A to B. That's their competitive edge in these devices, not the speed of the algorithm anymore. So like guaranteed to visit fewer states is a good thing. Can be really a solution in a different computational class. I have a technique that is not p-space complete, but it's polynomial. And it works in most of the cases, but sometimes it doesn't, because your problem needs to be in a very specific class for my work to be able to compute fitness or precision. But if it is, it can be done very fast. Now, and so on, right? So this is theoretical without looking at CPU times. I'm not interested that it takes 2 hours to compute a result on a laptop with 4 gigahertz processor and 2 gigabytes of memory, right? It's just not so interesting to read this, because by the time your paper gets in the hands of the next generation of PhD students, their CPUs have 40 gigahertz, and their memory, like 4 gigabytes, is just one file, right? So don't do that. What is far more interesting, though, is to look at this type of evaluation of artifacts. And this holds for conformance checking, but it might even hold for a much larger class of problems. Is to look at axiomatic evaluation. What are the properties of the things we are developing? What properties should they have, and do they actually have those properties? And one of the first that looked at this was Nick Tax, and later, so the reference in the slides is also the work of Anja Siering. They looked at this problem and they came up with some axioms about fitness, precision, and generalization. And I don't have the time to go in detail to all of them, but I want to mention those for fitness, because those I think we can all agree on. Like, fitness should be between 0 and 1. That's easy. If we add behavior to the model, fitness should not go down. Like, for a given log and a given model, if I'm adding behavior to the model, fitness should not go down. Like, in the best case, I'm adding behavior to the model that's not in the log, so fitness should stay the same. In the worst case, I'm adding behavior that I already observed, so fitness should go up. Adding non-fitting behavior to a log should lower the fitness. If I expand my log with a sequence that is not in the model, fitness should go down. Right? It's intuitive. If one model explains more behavior than model M2, then the fitness should be higher. Right? I should be able to rank 2 models on fitness. We already did that a few times today. And if 2 models have the same language, they should be equally fitting. Right? Now, trust me, token-based replay and alignments don't fit this. They do not satisfy these criteria. Token-based replay does, if and only if we do not have tau transitions and we do not have duplicate labels, then it satisfies these criteria, but alignments do not. And the problem is in the last part. If I take an arbitrary process model and I add a tau transition from the initial to the final state, the final place, then I change the best of the worst for every single trace in the log. So my fitness actually changes while I've actually not added anything to the model, because I added sort of an empty trace. And that's a very tiny change to the language. I wouldn't argue that it's actually a change, and still I changed fitness for everything. So that is, unfortunately, they do not hold. There are similar axioms for precision, won't go through all of them, and for generalization, although for those we are not really sure what we want or need or mean, right? So there's still a lot of work to be done. But it's very nice to read a paper that says, I have developed a new metric for precision and it satisfies these axioms. So then you don't have to bother with computational complexity. Of course, it's nice to show that you implemented it and it works on a real-life example, but at least you thought about the properties you wanted, and that's what you designed the metric for. Yeah? All right. Now, metrics are great, axioms too, but in the end, it's about the process. I want to go back to this context. Why are we doing this? We are not talking about data and models. We are always analyzing processes. Just before this session, I was talking about like auditing and consultancy, right? Or advisory. You want to help companies find issues in their processes. They don't care that the fitness of the model you show them with the log that you have is 0.8. They want to know what is wrong with the remaining 0.2. Or you can help them to get 0.8 to 0.9, right? That's what they're looking for. So we are always talking about the process. And deviations come in different types. So here I have some pictures from the Netherlands. So this is actually the university campus, already an older picture, but this is a very common sight in the Dutch landscape. We have a bicycle path. We have a lot of bicycles, so we have bicycle highways. This is a bicycle highway. We also have a small path here, which is for pedestrians going over the bridge to our sports facilities. And then you have the path that people make because they do not want to go over the path that was made. They want to take the shortest route from A to B. They cycle over the grass dies, and you get what they call elephant trails. Completely unnecessary deviation, right? Because there is a path that you could follow, but you didn't. There are also necessary deviations, right? Again, if you're in the Netherlands, you might encounter occasionally stairs. Trust me, on a bicycle, going down these stairs, especially for the men, it's not pleasant. So, there are necessary deviations. Of course, you could argue that it's maybe unnecessary because you can also go all the way there and back, but you don't, right? So, there is a necessary deviation. Then we have deviations that interfere with the primary process. Yeah? This is not the Netherlands, it's Brazil. And this is a training field of the World Cup soccer 1 or 2 years afterwards. Right? So you see that the primary process is sort of interrupted by the deviations here. And then we have a funny picture. So this is like the type of deviation that is simply illegal. Right? Sure, you can park there, but maybe you shouldn't. Now, in the defense of the person parking there, when that car parked, there was snow covering the entire parking lot and there were no other cars yet. So I saw that in the morning and came back in the afternoon to take the picture. Illegal deviations. So we are looking at alignments, we're looking at comparing logs and models. So where are these deviations? Well, suppose we have our favorite example again, and this event log. Application submitted. We call the customer, so we do a tau step, we call the customer. Then we send the offer, and now the application gets cancelled. So how do we explain this? Well, we check documents, we reject the application, and we cancel the application. Optimal alignment, cost equals 2. Perfect explanation for this particular trace, right? But it's not the only one, because I can also do this. Application submitted. I did not call the customer. I also never sent him an offer, but I canceled the application. Yeah? Cost equals 2, optimal alignment. This is the explanation your child will give you if they broke something in the house. No, I did not do that. Yeah, I know you can see that it's in the log, but no, I did not do that, right? So which of the two is the correct explanation? And how do you interpret that? So, this one we saw before. So what is a log move? A log move suggests customer was called, it's in the data, but the model does not explain this. Doesn't seem to be a problem, right? So you want to look at these alignments and you want to really investigate this in detail and try to find a physical explanation. You have offer accepted and check documents that did not happen according to our log, but money was transferred later. So we already discussed yesterday that this is a real problem, right? So you always look into the details of these alignments. But now remember that we talked about the 4 types of deviations. Which of them is what? So here we have, you call the customer, even though the model says you shouldn't. So apparently, we couldn't do things the way we should, but we did them anyway, right? Nobody forbids me to pick up the phone and call a customer. That's how we should do things, but we didn't do them. I remember that we had an overview of this yesterday. This is why we have all kinds of stupid rules. So why would I check documents and reject the application if in the end the customer wants to cancel it? What kind of stupid rule is that? Why don't I just cancel the application and forget about it? Or, well, there are some things in the data. Yeah, they're exceptional. Yeah, I sent an offer, but you know what? Let's pretend it didn't happen. This is just an exception, and well, it proves the rule. So try to interpret these things always at the process level. And I want to show you this practical example. So I'm going a little bit into the question time, but I started late, so that's okay. I want to show you this practical example. On the website of the summer school, the data and the models are provided, so you can actually do this yourself in Prom Lite. But I'm not going to do a demo. What I'm looking for is, right, you take the BPI challenge data set that is available on the website. Don't take the public one. Take the one on the site of the summer school. There's some sorting issues that I worked out. But it is real-life data taken from a real bank, right? There is nothing left out or introduced on purpose. This is actual company data from an actual Dutch bank back in 2012. We have process models. Those we made ourselves based on discussions with that bank, but I made them. So these are Petrines, they were not discovered. I made them by hand. And we basically understand the process, right? It's a loan application process that we talked about already for some time. And if you then do alignments in Prom, this is what you get. I highlighted 2 problems here. One is offer sent back. So this is the moment that the customer received an offer. They need to send it back either with a signature, accepted, or with saying, I want a different offer. So either the process goes to further processing, or it goes back in the loop we saw before, right? But now it's a slightly larger loop because otherwise it doesn't fit on the slide. The purple here indicates that there are a lot of move-on models here. So very often that transition happens in the model, but it's not recorded in the event data, but it should happen. The same holds here. We have 3 cases where offer accepted did not happen, but A activated did. And A activated means application activated, money is being transferred to the customer. So how do we interpret this? So there is actually 3,500 cases when offer sent back is a model move. So we started looking for the physical explanation, right, in the underlying process. What's going on here? It's a funny story. So now let me just tell you before I put it up. In this bank, the process is as follows. You submit a request for a loan, and then the bank processes that at some point makes you an offer on the phone. So the system says, computer says you can make one offer. You select from, like the call agent selects from a bunch of offers depending on the amount, the payment scheme, monthly payments, and so length, duration, and then tells the customer, this is the offer I can give you. And then what a customer does on the phone is they say, yeah, I like that offer, but do you have another one? And computer says no. Right? So the computer says you pick one offer, you print it, put in an envelope, send it to the customer, so the customer can respond. And if he sends it back, say I want a different one, then you go back and you take another one. But you're on the phone with the customer. So the call agent figured out very quickly how to solve that problem. They select an offer, print it, put it in the envelope, cancel the offer, print out another one, put it in the same envelope, send it to the customer. And then the customer sends it back, in the best case, it's the last one you printed. In the worst case, it's the first one. So you have to cancel the offer, select the other one that you already printed, you print it, throw it away, you take the one with the autograph on it, and then send that out for further processing. Right? A clear example of computer says no. The company found this, they realized that maybe they should change this, so it took them 3 years to do this, but in the end they bought a system where you can have multiple offers. In the BPI challenge data of 2017, you can see this. For process mining, it's a complete nightmare, but Dirk Valand will tell you more about that later this week. The other one is much more interesting. 3 cases where a loan was activated, money paid, but the offer was never accepted. 3 loans totaling 63,000 euros. Especially the top one has 109 events, indicating that after the loan was activated, they tried to reach this customer by phone, saying, we do not have your autograph for this loan, but we sent you 18,000 euros. Can you please send us an autograph, right? For a very long period, they tried calling the customer. Not sure if they did in the end. But we talked about compliance and conformance compliance just before. The probability of finding all 3 of these cases in a random sample of 3 is practically 0. Even catching one of them in a random sample of 10 cases is only 0.25%. So if an accountant looks at this data, they take a random sample of 10 of these process instances, they go through the details and they say, you did a brilliant job, bank. Right? Nothing went wrong here. My statistics tell me that nothing was wrong. But there's still 63,000 euros missing. For a bank, it's probably pocket change. But it's really not. And with conformance checking, you would find this. Even finding one of them is 1% if you focus on the activated applications only, right? So you leave out the rejected ones. Then, yesterday there was a question on, but there's more than control flow. Yes, there is. So here is an example of some deviations that are not directly control flow problems, but they are deviations. So who remembers what this process was about? Small consumer credit between 5 and 50,000 euros. The 50,000 is not chosen arbitrarily. There are some legal reasons why it's 50,000. Yet there are 4 activated loans that go over the 50,000 euro limit. So this is odd. 99,000 euros, even 2 offers made over a week apart. 60,000 euros. Offer was made and accepted within a week. Right? So these are not control flow issues. They fit. The model is nice, but still there is a problem with this data. And you can find this by digging into the details. You could find this with alignment techniques if you include the data perspective. We didn't talk about that, but there are techniques available to also include the data perspective. Felix Manhart, for example, worked on that. All right, so to conclude today. We are looking in process mining for insights into processes, not for getting the best model with fitness, precision, generalization. We're looking for insights. It's all about the process. So fitness, precision, generalization, simplicity, all these metrics, they help understanding how well a model explains the data, but in the end, you always need the human to investigate the details. And alignments help this human to focus on where the deviations are. And not necessarily in the best way, because there may be multiple explanations for the same execution sequence. But at least the alignment that you get will help you to check with the process owner, saying, well, what happened here? And maybe the explanation the process owner has is different than the one the tool gave, but at least you have the right discussion about the right part of the data. That's it from my side, so we still have some minutes for questions left. I see a hand in the back.
Thank you for the very interesting talk. From a practical perspective, when you're calculating these quality dimensions, should you calculate them on the same data that you're training the model on, or should it be done on an external validation set?
Very nice question. I left the sheet out, but maybe I should not have. So what happens if I calculate it? Suppose I do process mining, right? I take a sample, let's say 90% of the data, I discover a process model, and then I compute fitness on the remaining 10% of the data. What am I then validating?
Generalization.
Not quite. I'm validating the generalizing ability of the process discovery technique that I used. So I'm not evaluating the model anymore. I'm evaluating the technique that produced the model. It's a very, very subtle difference, but the moment you start thinking about k-fold validation in the context of process mining, you're no longer validating the result, but you're validating the technique that you used. And that's why we do this in data mining. Because in data mining, we validate the technique that we use to generate, for example, a prediction model. What we want is the correct mechanism to actually instantiate this prediction model. And then we put the prediction model into practice and say, this one will predict what your customer is going to do next. But we're not making prediction models. This is not predictive statistics. This is descriptive. So yes, you should test this on the data that you use to generate the model.
Okay, thank you.
Right, so the question here was what does it mean if we have models with the same language? We typically mean that in event logs we're looking at sequences of activities, right? So there are many models that can produce the same sequence of activities, but have a different structure. Now you saw before the model with all the sequences. If I add the one missing sequence to that model, then I have let me put the slide back, it makes it easier to explain. Just a bit further, where is it? Here. If I add the one missing sequence we identified to this model, so A, C, G, H, F, I, then model A and C have exactly the same language. They can produce the same sequences. But they have a completely different state space, right? Because this has all unique states for every trace, and that one just has a very compact search space, state space. So the language of the model is all the sequences they produce. Other questions? Yeah.
Thank you for the interesting presentation. Maybe a little bit of clarification. At some point in the presentation, you mentioned that practical evaluation is not very supported in the academic sense, I assume. But then in the end, you mentioned that we want to get insights, or the main goal of conformance checking is to get insights and to find practical value. So in that sense, in the industry, the axiomatic evaluation, it doesn't have that much value. Or how do what is the...
That's true, and I think that also nicely is shown in commercial tools, right? If you look at UiPath, for example, but also what Sander showed in the inductive miner, you have these red arrows that say, well, something is different here, right? That is to guide the user to a part of the event data where the data and the model disagree on something. So the proof of that being a correct conformance checking tool or technique would require proper A/B testing. That's what these companies do, right? They go to their user base and they say, well, you try to find issues and you get this tool without the red arcs and you get the tool with the blue arcs and you get them with the red arcs. And now see who finds the problem fastest, and if that's the group with the red arc, then that's the thing you introduce. You're not evaluating the underlying technique, you're evaluating the user interface. which is perfectly fine if you're selling the user interface, right? But as academics, I want to be able to guarantee that if I say this log fits this model, or this part of the log fits this model, that this is also actually true. So, and if I say this fitness is 90% and this fitness is 95%, then I would like it to be the case that the 95% is actually a better fitting model, and not a model that actually has the same language, but the technique just fails to recognize this. So, from a practical point of view, the user interface is much more important. Guiding this user to the deviations is important. What would be deadly for, and that's also what these companies struggle with, what would be deadly for a commercial company when you do conformance checking is to say there are no deviations, and then somebody finds one, right? The other way around is okay. If you say, well, there are some deviations here, and then you look in detail and say, but it's not deviating at all. What this stupid tool has a bug? Hey, and then it will be fixed. But the other way around, that is really problematic, especially when you go to, let's say, compliance checking, accountancy. Immediately you lose the trust of the customer and you can start over again. So yeah, for the academic and commercial perspectives are slightly different when it comes to evaluation. Oh, we're done? Well, maybe one more then. One more in the front. Right. I like how the minutes here are flexible. It's okay. Yeah.
Okay, I think I have some kind of journal question. Like whenever we are doing conformance checking, we are taking event log as an input of a business process. Okay, so I was thinking that every process have some model when they implement in order to start their business. Mm-hmm. And why not, instead of getting the event log, we should directly deal with the model, the actual model of the business, in order to get some insight about the model and the structure of the business, instead of just relying on the event log and to trace the behaviors in the event log, which is somehow unreliable, and the behaviors are different from each other. Why not take the exact model from the business and then compare it with the event log and the model? It would give some.
I understand the question, and so I think there's two parts to the answer. So one is definitely, if you have an exact model specified somewhere, use it, right? I'm not advocating you should use discovered models. I'm advocating you should use models, but how you get them, right? You can also do man-made models. What we often do in practical exercises is you do discovery and you take that as input and then start manually updating the model to be like nicer, closer to reality. But you can also use process specifications, handbooks that are available in companies. What you'll see in practice is that they have absolutely no relation to reality. So a handbook has been written purely to be put on the shelf. So it's sent to a panel of experts, and they will say, okay, you have documented your processes, here's your ISO 9001 certificate. But it doesn't actually require you, the certification does not require to also execute your processes according to the documentation. It just requires that the documentation is there. And this is, unfortunately, how it's implemented in practice. First, you try to follow the specification, but soon people start realizing, I can just put 2 offers in one envelope. Mm-hmm. And before you know it, every envelope contains 2 offers, but your handbook says this doesn't happen. And if you ask the people, they know that there is a handbook that they should not do this. So they will never say that they do this. They will say, no, we nicely follow the specification. But if you have one, sure, use it.
I think maybe at the theoretical level, it would be more better to start from the model of the business and the specification.
Sure, if you have it, please do.
Okay.
Please do.
I have another question, and which is related to the prediction of after. Yeah, I just wanted to know about prediction in conformance checking. That's all.
Yeah, so the work on the anti-alignment is trying to predict this sort of trace that you left out. That's the prediction task we looked at. For real process prediction, right? So when you predict the outcome of a process, or I think there's a session later this week on predictive process monitoring, right? Yeah. So.
Thank you so much. Thank you.
So let's thank the speaker again.
Thank you.